Okay, so this week we've been looking at assumption checking, residuals, and influence points. So let's now have a case study example of this. And the one we're going to do is cheese. So we've got this cheese data set. And what they did is they took various cheeses and they measured some variables. They looked at acetic acid, hydrogen sulfide, and lactic. And then they gave them to experts and they had to give them a rating on taste, where the higher the rating, the better the taste. So the idea is, how do these things, like these various measures, chemical measures we can do, affect how good a cheese is? So let's load some packages. We're going to do tidyverse and ggLM, and then we're going to read it in. Now in this particular case, the data is what we call a tab delimited one. So what I've done now, first of all, this here, you might go, well, what's that about? All that does is when I'm using a project like I'm here knows where this project is on my computer, like that. So it says you're in this particular place. It gives you the absolute reference. And then what I can do is I can then say, well, in this, there's a folder called data, so that gets data. And then in this, there is cheese.txt, and it gives me the link. Now, why that's useful for me is I've often got lots of subfolders in my stats modeling, and then when I'm running my R Markdown, it needs to be able to find them. And you'd have to set it up so it's referenced automatically, and getting the reference in. When you compile it, it wants is a reference from where it compiles from. But when you run it, it thinks it's in the main project. So I just find the here helps me. So there you are. The next thing we've done is we're doing read delim, because there's a delimitation, and this is just the equivalent of a tab. So basically it's saying, here's where you find the data, read it in, it's got tabs, and when we run that, it tells me that it's got a load of doubles, 4 doubles. These are the column names. And when we look at it, so we've got taste, acetic, hydrogen sulfide, lactic. Cool. So we've got our data in. As always, the first thing we do is EDA, Exploratory Data Analysis. So let's do a bit of skim, see what we've got. So we've got 30 subjects. In this case, each one's a sample of cheese. 4 columns. They're all numeric. Again, we've got no missing data. It's all complete. We've got a mean of taste of 24.5, standard deviation of 16.3. Here's our stuff. And we've got our little histograms of each of the things. As I said, the next thing I normally do is I quickly do a histogram of my response variable, in this case, taste. It's not a lot of data. It's hard to see patterns, maybe a little bit right skewed. I'll tell you what we'll do is we'll just quickly copy this down. I'm going to change that to a density plot. Yeah, a little bit right skewed there. Unimodal, maybe almost, you could almost start to argue there's another mode appearing here. So unimodal, right skewed. Anyway, so we might have to, when we get to our normality, just check that. So now I'm going to use my little trick to get lots of scatter plots. So here we are. We have the scatter block of taste against acetic, taste against hydrogen sulfide, taste against lactic. In all of them, we have a positive slope. So as they increase, it increases the taste. These hydrogen sulfide and lactic seem to be ones closer to the line. This acetic seems to be a bit more widespread, but not too bad. So we're going to fit a model. So you may not see this before, but I've just got basically taste tilde dot. What does that mean? Well, the thing on the left, taste, is the response variable. The dot is basically saying, give me main effects for everything else in this data frame that's not taste. So dot is a shortcut for everything else. So if I run this, and then we do our summary, let's have a look at our summary. So we've got, here's our predictors. We've only got main effects, no interaction terms. That's all looking pretty good. Acetic, as we said, not strong, doesn't seem to be significant. Hydrogen sulfide, definitely significant. Lactic, yeah, just significant. Okay, but what I want to focus on this time, I'm not going to try and clean up this model, make it better. I want to focus on the residuals. So there's a couple of ways you could get residuals out. You could just type the residuals command and you could give it your model. So what's it called? Cheese LM, and that would get your residuals. There's another command that will get you standardized, but I actually really like, we've used Broom before, we used Broom Tidy and Broom Glance. Here's the third one, it's called Broom Augment. And when you run this, what it does is it augments your data frame. So it's taken your data frame and it's added fitted, residuals, standardized residuals. Your hat is your leverage. You've got your, I can't remember sigma, we'll have a look at that in a second. And we've got our Cook's SD, our Cook's distance. If we just quickly augment, it'll come up, it says you have different ones. It wants the linear model, so let's do the linear model. And if we go down, so what have we got? We've got Cook's distance fitted, diagonal of the hat matrix, which I said. Lower bound interval for fitted values, residuals, standard errors of fitted values. Which ones did we get? Sigma, estimated residual standard errors when corresponding observation is dropped from the model. Okay. Standardized residuals, upper bound for fitted values. Well, I don't have any. Do we have any? It doesn't give me the upper and lower on this one, which is interesting. But the rest looks pretty good. Now the problem is I also want to have studentized. Now to do that, there's a studentized function in the maths package, and I'm just going to add this as an extra column. So if we now run this command, you see that it's done everything else, and also it's added in this extra one. Let me actually prove that that's the case. If I run it again, there you are. I've now got studentized residuals. Remember, that's the one where you remove that point, fit the model, and then look at the residuals for that one. So let's run this whole thing. There's my data good to go. So what we're going to do is we're just going to quickly explore these three residuals and the patterns between them. So first of all, let's have a look at, this is our standard residuals, here's our standardized. And you can see this is pretty much the same. The only thing you do is it all lies on a line. You'll notice the scale is very different. This is going from -15 up to 25. This is now standardized. It's basically going from -2 to 2. We'll look at the residuals versus the studentized. Again, reasonably similar. There's not a lot of, I think if you saw a big difference in one of these, it would indicate that there's a point there that has, influence on the model. So now we'll start doing what we do with our plots. So we're going to start with the standardized residuals, then I'll look at the studentized. So remember, for these, to check them, what you should do is first of all, plot them against are fitted. So here's residuals versus fitted. You're looking for any sort of patterns in there. If you wanted to add something to check for patterns, we could do the old lowest line. That's a little bit extreme, but you've only got a small number of points. And I honestly don't think there's a lot of pattern there. I think that's been a little bit over the top. I wonder if we could change span equals 3. Yeah, if I just straighten out a little bit. Yeah, that's looking a bit better. But the other thing you should do is you should plot your residual versus each predictor. So we've got the C-tick. Not too bad, can't see any obvious pattern. Again, the problem is we don't have a lot of points in this. Versus hydrogen sulfide versus lactic. Now, we could also do a similar thing with the studentized residuals, which is probably your best bet. It's just a lot of people don't, because the residual standard one is the ones that's not the standardized, but the common one is the one that is default. Again, I'm looking for any patterns to some extent. I can also look on these for homoskedasticity, but I'm generally looking to see if there's any patterns, anything I need to improve my model. But let's just recap ourselves what would happen if we did the normal plot. Well, first of all, this would give you your residuals versus fitted. The residuals there is your ordinary residuals. It does your standardized residuals. Notice it's doing that for your normal QQ plot. That's looking pretty good. Remember we had that right skewed? Doesn't seem to be affecting it too much. That's not too bad. Here you've got the square root of Studentized Residuals for your checking your homoscedasticity. Notice it increases slightly as your fitted values increase. So a little bit more noise for the larger values of taste, but not too bad. And this is your influence plot. So what we're looking here is, first of all, you've got your leverage on the x-axis, your standardized residuals on the y-axis. Here you've got 0.5. Remember, we're looking for roughly any Cook's distance greater than 1, and that all looks pretty good. The other plot you can do is, with all these plot, it just gives you all 4, but you can actually ask for individual ones, and I'm going to ask for number 4, which is this one. What this is every observation, and it's got its Cook's distance. You can see they're all less. They're all about 0.2 or less, so there's no problems here. But it is quite a nice way to quickly see, you know, the main points and drag them out and have a good look at them. The other one is the GGLM. This does them automatically. Again, we do see there's a bit of curvature, maybe some heteroskedasticity. The residual versus fit looks fine, normal QQ. The only problem with this plot, I mean, I like these plots, they're nice and prettier than the other ones, doesn't have your contours on it. That's the only thing. Should be a bit of a shame, but other than that, not too bad. So there you are. There's a quick analysis of cheese and a look at your assumption and influence diagnostics. See you next time.